Hi and welcome everyone. In this video, I want to go over the linear differential equations of higher order and the preliminary theory. So first of all, the goal of this chapter or our primary goal is this chapter is to find general solution of linear higher order constant coefficient ODEs. Now, before I continue this lecture, I decided to do some definitions for you at the end. So let's go over those, and I'm gonna put this in a couple of lectures, and so you can really understand the fundamentals of this topic. Now let's talk about the theory of higher order differential equations. We're going to talk about this. This is probably part one. So, but before we do this, let's go over the notation and types of higher order differential equations. And I think if I do this with examples, then it's you're going to understand it better. When we say higher order, we learn how to solve first order differential equations. That's the first order is only has y prime, but here we're going to see higher order like triple prime, the second derivative, and all that. Now this, we're not going to solve those, but I just wanted to understand this equation is a third order homogeneous with constant coefficient. Now third order because the degree is 3, homogeneous because it equals to 0, and with constant coefficients, that means those numbers, these are just numbers. Now if we take a look at the second one, this is a fourth order homogeneous with variable equations, variable coefficients. Variable being that means the coefficients are functions, and it's fourth order because we can clearly see that, or you can just put that for fourth order. I think it's okay. And the third one, let's go over the third one, y double prime plus 3y prime plus x squared plus 1y equals to x cubed plus 1. This is a second order we see here, and that's not non-homogeneous because equals to a function, and with variable coefficients because this coefficient here is a function itself. And finally, we have 2y triple prime plus 3y prime plus 6y equals to ln x. This is third order, as we can see, and this is non-homogeneous because equals to a function and with constant coefficients. As we can see, these are all constant coefficients. Now, general notation, a homogeneous equation, you can use the general way of writing this is a sub n of x times d to the power of n y over dxn, and plus a sub n minus 1 x d to the power of n minus 1 y dx to the power of n minus 1, and so on until a sub 0 xy equals to 0. Now this part here, we can call it L of y equals to 0. So this is homogeneous because it equals to 0. And same thing when equals to a function, you can write this as L of y equals to g of x. And I am going to talk about this. So now we know the difference of homogeneous and non-homogeneous equation. Let's talk about differential operators. A differential operator, the notation, you write it as dy dx equals to d sub y. So if you have an equation like that, y prime plus 5y, y double prime plus y prime plus 6y equals to 5x minus 3, you know this is non-homogeneous. If you want to write it as a differential operator, then you write for double prime, you say d squared plus 5d plus 6 times y equals to 5x minus 3. So just a notation that's going to help us to solve those. Differential operators in calculus, differentiation is often we know denoted as capital D. Do you see this in calculus? Or dy dx equals to d sub y, not d times y. This is d sub y. The symbol is called the differential operator because it transforms the differential function into another function. For example, d cosine 4x, when you see this, that means you just take the derivative of that function and you get negative 4 sine 4x. And d of 5x cubed minus 6x squared, you just take the derivative of that function and you get 15x squared minus 12x. And again, higher order derivatives can be expressed in terms of d in a natural manner. So, you know, for the second derivative, you just take the derivative of the first derivative, and that gives you d times d squared over dx squared. And if you're dealing with differential operator, you can say d of d sub y, and that's going to give you d squared y. And in general, that's the notation you have. The nth derivative can be written as d to the power of n times y. Now the general notation, so the general operator notation, so this is L. So when you have this differential equation, so you can write that as L of y equals to 5x minus 3. And nth order general differential operator or a polynomial operator is a linear operator and is closed under addition and scalar multiplication. And again, this is from linear algebra. So, but don't worry about that right now, just a definition I put here for you. Any linear differential equation can be expressed in terms of D notation. So, and we saw that again. If you have y double prime plus 5y prime plus 6y equals to 5x minus 3. So you can write that as d squared y plus 5d plus 6y equals to 5x minus 3. And you can factor out the y and write it like that. Now, we are going to go over this, and I'm going to do another video for that. But before doing that, it's good to know they're from linear algebra. There's some helpful topics, and please watch. I uploaded a couple of videos from that. Just watch them, get an idea. One is to know about linear combination of vectors. You know that you have a vector, you can write that as a linear combination of other vectors. It's written like that. And there are a couple of short videos that I have uploaded. Watch those videos so you can get an idea. Then linear dependence and linear independence. Linear dependence, you say two vectors are linearly, these vectors are linearly dependent. Basically, they're kind of in the same direction. One can be written as a linear combination of the other one. So here, if you look at this, you can kind of say the v equals to 2 times u. So then that happens, then they are linearly independent. These two vectors are not linearly independent, and you say they're linearly independent. Simple examples in R2, but it's gonna help you because you have to know sometimes the solutions of higher order differential equations have to be linearly independent. How do you prove that? You use the Wronskian. So let me go over this also. So if you have a set of function here, so and to n minus 1 derivatives, if the determinant is not 0 for at least one point in the interval, then the functions f1 of x, f2 of x, f3 of x, and fn of x are linearly independent. The way you do that, the example is very easy to see. So you have the set of functions, you calculate the Wronskian. So you put your functions here, and you take the first derivative, and then the second derivative until f to the power of n minus 1. and you calculate the determinant of that. That's the notation for the determinant. And if that's not equal to 0, then you can say they're linearly independent. And here we have it, criterion for linearly independent solution. We have, these are the solutions of a homogeneous, don't forget, linear nth order differential equation on an interval I. Then the set of solutions are linearly independent on I if and only if the Wronskian is not equal to 0 for every x in the interval. So that should not, that means that determinant should not be equal to 0. This is a simple example. Just know how to do this, and probably with 3 by 3 also there's an example. Let's say this is the solution. We have two solutions for a differential equation. The first solution is e to the power of 3x, and the second solution is e to the power of negative 3x. If you want to know if these are independent solutions or linearly independent solutions, so you calculate the Wronskian. You put the factor, and then you calculate the first derivative. So here you get a 2 by 2 determinant. Then you calculate the 2 by 2 determinant, and I put the formula here for you. If you have a 2 by 2 matrix, the determinant is just a times d minus b times c. If you do that, you get a to the power of 3x times negative 3 e to the power of, not a, but e to the power of 3x times negative 3 e to the power of 3x minus that times that, which I wrote it here. And again, e to the power of 3x times e to the power of negative 3x. And that should be negative. Is going to be e to the power of 0, which is 1. So the solution, if you calculate, is negative 6. Then you say, if you wrote these two solutions are linearly independent. Again, watch the lecture on linearly dependent and independent. Just have an idea how that works, because later on it's going to be useful. I think that's good enough for this video. On the next video, what I'm going to do, I'm going to go over the solutions of higher order differential equations and explain. But if you watch those videos first, then it's gonna, the explanation of the next video is gonna be much faster and easier for you. Thank you for watching, and I'll see you all in the next video, or you will see me in the next video. Have a good one.